right, so welcome everybody to the second last day of the ItaCa Workshop. We begin with our second invited talk given by Marco Maggesi from the University of Firenze. Marco will talk about categories and back-categories in univalent foundations. So Marco, please go.
Thank you. Thank you for giving me the opportunity to be here for this meeting. Was a very pleasant opportunity to meet people, and also even if I'm from near university, this is my first time at the Department of Mathematics of Computer Science here, and so I'm very happy to have this opportunity. And this is a joint work with a bunch of people: Benedict Harens, Dan Frumin, Niccolò Veltri, and Niels van der Weyde. Was an effort both from the theoretical side and also the implementation side, because this is about doing category theory in univalent foundation. Personally, I didn't participate in the development of category theory. I worked only on the part related to bicategories. But anyway, many phenomena that I will speak about this talk are equally interesting in categories and bicategories. So I will speak of both in some sense. And so the plan is roughly this one. First of all, we will speak about categories in a univalent foundation, and this is related to this work of Harens, Kapulkin, and Schulman about the univalent categories. And so what is interesting here is that you are doing category theory in a different foundation of mathematics, which is not the classical one, set theory. And so the thing that you want to do is devise the right notion of category in these settings and compare with the classical one and so on and so forth. And as we will see, we come up with a notion of univalence for categories, so univalent categories. And it turns out that proving that a category is univalent can be a difficult task. It is often a difficult task. This is somehow expected, because what you do when you do univalent foundation is doing something in intentional mathematics. So objects carry more information in some sense. They are richer, we could say. And so it is also, you can expect that you have more work to do, even for redoing things that mimic the classical constructions in classical mathematics. And that's why there is let's call it a device, which are displayed one categories, which help to construct univalent categories. It's a problem of having a pattern for doing what you do in the classical mathematics in the univalent foundation. And then I will speak about bicategories and something which is specific to bicategories, but many things are actually the generalization of what to do in one categories. So some motivations, perhaps we don't need a lot of motivation for doing this. But anyway, Of course, there is the general goal of developing mathematics in the univalent foundation, which can be interesting for many things. But perhaps we have more specific motivations. And so one is still general motivation is study categories with structure. If you do study set with structure, you do category theory. And if you want to study categories with structure, you need something more like by categories. But in particular, we had two main things that pushed us to start this work, which is about doing initial semantics. We already used in the past the computer for certify some of our theorems in initial semantics. So I think you know perfectly what initial semantics is, but if you don't know, first, it's not important because I'm not going to speak about initial semantics. And second one is simply the fact that if you want to speak about abstract syntax, usually you come up with some kind of notion of initial object in a category, and this is a very general framework. And we did some work on using categorical structures for doing formalizing initial semantics for high-ordered languages, and the prototype is lambda calculus. And we happily used several systems, Coq with Unimat, HLite. But if you want but most of this work has been done for untyped syntax. And if you want to work with typed syntax, one thing that you may want to use is categories, and so you end up with initiality in a bicategory, and that's one of our motivation. And another thing is have a tool for studying higher inductive types, at least one level of higher inductive types. This is the right context for studying these kind of things. Actually, they are very, very related. So it is more or less the same goal seen from two different settings, two different perspectives. OK. So let's start with the case of one categories. And let me review some general things that have been done in the context of formalizing categories to the computer, and in particular, formalizing categories in dependent type theory, which is the point of this slide in some sense. A very classical approach, I think, used already in the early 90s is about using setoids. So the idea is that you have a type C0, which is the type of objects, and a family C1 for arrows. So it is a dependent type, but this dependent type gives you setoids. So a setoid is just a type together with an equivalent relation. And the idea is that you explicitly give a way to compare arrows. And of course, you have the identities in each arrow space. And when you do the composition is something like this. So you take an arrow from A to B and an arrow from B to C, and you get an arrow from A to C. So nothing special here, but you see, I don't use the arrow of the types. I use this constant map because when you build something like this you have to specify that the composition is compatible with the equivalence relation that you give. So this is the notion of arrow type, but equivalent with the setoid structure. And then you have to specify the category laws up to the setoid relation. And when you do this at all levels, so you do this for functors, natural transformations, and so on and so forth, you end up in what people sometimes call setoid hell. The setoid hell is that you have setoids everywhere, and everything is hard to say in a concise way, etc. Can be a problem that can be solved, for instance, with some engineering or with a specific theory for this, in some sense. So it's not something inherently wrong, but so has problems anyway. So another approach is to use plain types, but add some kind of axioms for not having this kind of problem. So you still have a type for objects. Now you have a type family for arrows, and this is a nice type family as in the usual sense. You have the identity. The composition now is done by arrows between types, and this is nice. And you specify the category laws. However, if you use the identity type to give the equation that you need for the category laws, the problem is that the identity types can be inhabited by more than one proof for the same equation. And so you end up with something which is like a bicategory. It's not a true category in some sense. Can work for some specific task. You can even modify your type theory. For instance, you can add the uniqueness identity principle, which collapses the identity type. And so it's something that, again, it's something that you can do. It's not wrong per se, but if you have another philosophical picture in mind, what you notice that this is trivialize the homotopic interpretation of the identity types, and this is something that you don't want to do. So let's start to speak about the definition that we use in Univalent Foundation now. And probably you know what the univalent axiom and all that is, but let me recap very briefly. So the idea is that the inhabitants of the identity type A equal to B are what we call paths, which is just a metaphor. The name path comes just from a metaphor that comes from topology and homotopy theory, and which encode an information that we understand as how we can deform, if you want to speak in topological term, or how we can transform A into B. And if you accept this idea, you think that what you have in this type, it's not something that you want to collapse, it's something which is precious in the spirit of the intentional mathematics, and something that you want to carry on, have and manipulate and exploit in some sense. So the univalence axiom can be stated in this way. you want to, you have two notions of sameness in some sense for types. And you have the identity of types in the sense of the identity type, in sense the identity type on the universe. And you have equivalence of type, which intuitively is just bijection. If you collapse in set theory, it's just bijection. And so obviously you have a map ID to AQV, which goes from A to B equal to B to A equivalent to B. And the univalence axioms say that this map is actually an equivalence. So you cannot distinguish types which are equivalent in logic. So this is the general spirit of univalent foundation. And when we come to category theory, what you can say that in category theory, you have the same problem. You have two notions of sameness. One is the identity, the other is isomorphism of the category. And if you use a traditional foundation, these two notions are different. Okay? And the idea is to give a definition in a univalent foundation that makes these two notions coincide. So we can say that the univalent axioms makes types behave categorically, as I said, in the sense that you cannot distinguish types which are isomorphism. In the case of types, the isomorphism is equivalence. You cannot distinguish types which are equivalent. And the univalent categories are defined in a way that they behave categorically. So you cannot distinguish objects which are isomorphic. So this is the definition. And you have C0, which is the type of object, as before. Here you have a family of sets in the homotopical sense, which means that you assume that the identity type on arrows is a proposition. So you don't have two different ways to prove the same identity of arrows. And in some sense, this is made to make sure that we are speaking of the classical definition of category. It would be interesting to drop this hypothesis and use general types. However, you end up with a much more richer and difficult theory. So this is the way to recover exactly the theory you had before. It's something that you can drop, but it makes sense to drop, but gives a goal which is much more difficult. And then you have the identities of the category and the composition of the category as before. And you have the usual category laws and the univalent condition. So the univalent condition is similar to the univalent axiom, but stated in the language of the category. So you have an obvious map ID to ISO that, given the equality of two objects, gives an isomorphism of the two objects. And we say that the category is univalent if this ID to ISO map is an equivalence. And what I said should make you believe that this is a natural definition, but anyway, we have some theoretical results which says that this corresponds to the, in some precise way, to the classical notion of category theory in set theory. for instance, you can reason like this. You think homotopy type theory like the internal language of some kind of higher topos, and you have for this tuple you have several models today. One classical model is the simplicial model of Voivosky, and in this model you see that univalent categories correspond to truncated complete Segal space, which are equivalent to set theoretic categories. So in this sense, this theory is speaking, even with another language, exactly of category theory. Okay, so as I said, there is a problem, which is the fact that when you want to prove that a category is univalent, it can be a hard task in general. And as we saw in the previous slide, the proving univalence is more or less, in very roughly speaking, is about finding an inverse of a map in some sense. And so I would like to use this analogy. Say you have a map F from A to B. Think F as our AD to ISO, for instance. And you have to find an inverse of this map. So perhaps if this F is very complicated, find the inverse can be very hard. But sometimes this F can be decomposed in a sequence of applications, F1, F2, etc., where each intermediate step is simple and the inverse is easy to find. So the idea is, whenever it's possible, to split your transformation in simple transformations that are easy to invert, and then in this way compute the inverse. And this is exactly what we do, even if the language makes this a little bit obscure, but the idea is this one. So to make an example, let's say that you want to construct the univalent category of monoids. So actually you have that monoids form a category, and this category is univalent. But you can easily define the category, then you have to prove that it is univalent. It's not too difficult in the case of monoid, but anyway, we are looking to the general picture. So there is an approach which consists in define monoids, define morphism between monoids, prove that they form a category, then prove that this category is univalent. And there is a second, and this can be difficult when you arrive at the end that you have to prove that your object is univalent. The second approach is about reasoning at the category level. So you don't build single objects and see what property they get when they are together, but you speak about the categories since the beginning. So you start with the category of sets, which is already univalent. And at each step, you add a small piece, and you look that it is still univalent because the previous step is univalent. So for instance, you add points. You add points because you want the identity of the monoid. So starting from sets, you go to pointed sets. And since sets are already univalent, it's easy to prove that pointed sets form a univalent category. Then you add a binary operation for the product. And again, you see that this new layer doesn't change the property of being univalent. And then you take, at the end, the subcategory of monoids. And again, since you take a subcategory of a univalent category, it is easy to prove that it's univalent. So there is, this is a smooth path that gives you the object that you want. Okay. The problem is, how do we make this stratification? So which is the tool that allows us to build categories with strata and prove that they have the right property at the end. This is the notion of displayed categories. So displayed categories, the idea is that they are like, it is the same information as a functor in some sense. So a displayed category D over a category C is the same thing as a functor D prime arrow C. So the displayed category is the same as the pair D prime P, but this information is organized in a different way. And this perhaps makes the notion less interesting to your eyes, but you know, when you are doing formal, intentional mathematics, definitions are important. If you work with a definition or another definition, it's not the same thing. This is, in some sense, the right way to organize this knowledge when you do this kind of operations. So, in theory, it's the same as a functor. In practice, it is more useful in this context. And this is a very rough picture. Sorry, I'm not very... I don't do very nice picture, actually. But so imagine that you have a category C. And so here you have a lot of, in general, you have a lot of objects and arrows, but I draw just 2 objects and 1 arrow just to reason about. And what is the displayed structure? The displayed structure are, in this case, a family of types of displayed objects, which are indicated in this case by the 2 triangles. So every object has a type of displayed object on top, over it. And so, for instance, the A prime here is something that I call a displayed object over A, and B prime here is a displayed object over B. And moreover, you have a family of displayed arrows. So given the 2 displayed object A prime, B prime, and the arrow here between the underlying object F, you have a type of arrow between the 2 displayed objects, which can be empty, of course, but say you have an arrow, it can be represented like this. And you say that F prime is a displayed arrow on F. And this is the data of displayed category. So when you have a displayed category, you can build what is called the total category. And the total category, it's so as I said, displayed category is not a category itself, but you can build this notion of total category, which is usually denoted with this integral. And you have a projection of the total category of the displayed category D to the base category C. And how it is done? It's very simple, of course. You have to, sorry, I forgot to say something. Of course, even on the displayed category, you have laws. You have the displayed laws of the category. So you have associativity between you have the structure of composition and identity on the displayed objects. And you have the laws of associativity, left and right identities that you have to impose on this structure, of course. And if you do that, if you just take pairs of an object and a displayed object, and this is will be the objects of our total categories, and the pairs of an arrow and a displayed arrow over it, what you get is a category. And the nice thing is that there is a very natural condition on the displayed category, which says when the total category is univalent. So this splits nicely the problem of univalence. You have a category, a base category C, which is univalent. You have a displayed category, which is displayed univalent. And when you take the total category, you are integrating somehow the structure, and it is univalent. So this is what we do, for instance, in the example of monoids, but more or less the same thing is what you do in the case of other structure, like if you take groups, you can build the displayed category for groups over monoids, and in this way you can prove that the category of groups, you can build the category of groups and have almost automatically univalent. So it is a mechanism that we use everywhere. Okay, so let's speak about bicategories. We have this work that describes, which is both the theoretical foundation, but at the same time gives the pointers to our implementation of bicategories in Coq Unimat. So in the paper, we made a huge effort to make this usable for documenting the library. And each definition or theorem has this kind of links. If you click on the links, you go to a website where you have the code, the corresponding code. And so the first difficulty we had about bicategories is how to define bicategories, because a very simple and principled way to define bicategories is saying that bicategories are one category is weakly enriched on categories, and this is a very nice and conceptual way to give the notion. And can I click on the link? If you go to the NLab site and you see the definition, I hope to be able to go back to the slides. Okay, the structure of the page in the NLab site. They have a very concise idea, which says what I said, that they are weak to categories. It is a notion of weak to category. And here you have the description, the definition of bicategory. You say you have objects. For every pair of objects, you have a morphism. You have a space of morphisms, which is a category. And at some point here, it gives you what we call the unfolded definition of bicategory. The unfolded definition of bicategory is when you do the definition of bicategory without relying on the language of one categories. In some sense, you do the definition from scratch. And you see, it is something that if you want to be able to prove things in bicategories, you have to do once in your life, because you have to work with the explicit things that you have in the explicit structure that you have in your object. So here in this page, you see there is the structure. So you have a collection of objects. You have a collection of arrows, which is not a category for now. And you have composition, you have identity, and you have two arrows, of course, 0 cell, 1 cell, and 2 cells. And here you have the structure, the operation that you have. So the existence of identity for 1 cells, and decomposition for 1 cells, and the identity for two cells, etc., etc. You have those notions that you know, like associate or unit or etc. And then you have the properties. So here is the structure, and here is the laws. You have to give all kind of laws, including the famous laws like the pentagon, etc., and many other which are just the naturality of the construction we are using. So we realized that this was the right way to do the definition in the formal development. So even if it was possible, actually, there were already from another author present in the library a definition of bicategory using but we decided that it was not the right way to do this. And we used the unfolded definition. And this is somehow necessary because for many practical reasons. For instance, one thing is that you need to have this kind of data explicitly when you want to prove other theorems. But also, it is necessary because in this way, you can reuse the notation of one categories. It seems counterintuitive, but if you do it this way, you can start from the structure of one category, then add more structure, which is the structure without assuming the laws of the one categories, then add more structures using the same notation that you had before, and then gives the laws. And this way, you can integrate in a nice way the code for one categories and the code for two categories. So this gives a lot of work to do, of course, and for instance, one thing that we try to do is to prove the equivalence of the two definitions. Actually, in the previous page, there is something curious at the end. It is here it says it is quite possible that there are errors or omissions in this list, although they should be easy to correct, because of course it is a long list of properties and objects, etc. So if you look at our code, we can say that actually they made no mistake after all. But it's not so easy to prove the equivalence with every detail. And then you have to do some work for proving the so-called derived laws. For instance, one nice derived law is that the left unitor and the right unitor coincide on the one cells are the identity. So you start with the diagram on the top. You have the identity. One arrow on A composed with itself. And you can do two things: collapse the identity on the left with the left unitor, or collapse the identity on the right unitor. And so you have two ways to go to this arrow from A to A. And actually, you have that they are the same. But it's something that you have to prove. And one way to prove this is to do this in the context of monoidal categories, because your home space with the product form a monoidal category. And if you go to the work of Joyal and Strict about braided tensor products, there is a proof that involves at some point this diagram. And this statement is an easy consequence of the fact that this triangle commutes, where there is the question mark. And this triangle commutes because the rest of the diagram commutes. And the proof of everything, of the commutativity and the the corollary that left and right unitor are the same takes about half a page. And for us, just verifying this one, which is very easy in the sense that each square is some kind of naturality. You have just to give what you have to do, but it's not conceptually. When you have the picture, it's easy to do. This was the code to write this. So essentially, all this code is something that in the paper of Joyal Strict does not exist. Okay, they say it is easy, and check yourself. So you can imagine that this gives a lot of work to do. That's why we are 5 people to write this kind of this implementation. And okay, so let's try to finish in a few minutes now. When you want to do this is about giving the structure and the laws, but as for one categories, you have to give the definition of univalent by category. And the idea is more or less the same. The only thing that you have to care is that now the structure of by category is more complicated, and what you came up is this. You have a notion of local equivalence. So if you have 2 arrows F and G that are equal, you can have you can get you can see that they are isomorphic in the category of two cells. And local univalence says that consists in assuming that this is an equivalence of type. And you have a global equivalence, which says that if you have 2 objects which are equivalent, then you get an internal adjoint equivalent in the category. And what you impose, again, is that this arrow is an equivalence. And by categories, univalent if it is both local and global univalent. This is the definition. So it is more complicated, but it essentially is the same thing as in one categories. So about application and future work, in our we try to experiment our framework in a number of situations. I'm going to give some examples. So one example is the classical construction. So things that are very easy in some sense, the opposite category, the full subcategory, or the strict 2 categories. So when the laws of bicategories works strictly. So when the associator and the left and right unitor are equalities. And of course, the univalent by category of a univalent one category. And this is a kind of first check that your framework is consistent. And then some more complicated and more interesting examples is doing, for instance, the univalent by category of one types and the univalent by category of groupoids, and find the B equivalence between the two. I didn't give the definition of B equivalence, but it is the right notion for identifying bicategories. So you know what it is. And this already can give some results in the study of the semantic of higher inductive types. And of course, we have a notion of displayed by categories, and we use displayed by categories to build interesting univalent by categories. And for instance, we have the category of pseudo-functors, pseudo-transformation and modifications. And this was a very hard work, because again, to give you don't give the definition of pseudo-functor. You give the definition of the category that has as morphism pseudo-functors. So you have to build from scratch one object that, which is a category, that layer by layer gives the structure of pseudo-functor, pseudo-transformations, and so on. And starting from the univalent category of categories. So it is a little bit hard to see at which level you are and how to write all this, but it's just bookkeeping. The proof that it is univalent at the end is nothing at all. And we have the univalent by category of algebras of a signature, so already something about initial semantics. And as I say, the other kind of B equivalence, for instance, the univalent category of formal monads and the univalent category of Cleasley triples. And finally, some other things related to the study of abstract languages, like a category with families. And example like that. And also, there is the problem of saying when, if a category is univalent, what it's not univalent, what you can do. The problem is completely solved in the one category case. There is a process which is called Ritz completion, that given a category gives you an univalent category which is equivalent to the first one. And we know that it is possible to do the same thing in bicategories, but it is very, very complicated. So for now, it's not finished. And but we have some steps, because the idea is that you use the Yoneda embedding. And so we formalized the Yoneda lemma for bicategories. And we proved that every locally univalent bicategory is weakly equivalent to a univalent one. So the step that is missing is when the category is not locally univalent. So of course, there are many things that we can do starting from here. So finish the Ritz completion for bicategories is one. And prove the equivalence principle for bicategories. So proving that two bicategories are bi-equivalent if and only if they are equal. Study the semantic of either inductive types, as I said, and study other categorical structure. Okay, I finished. Thank you.
Okay, thank you, Marco. So, questions?
Thank you for the talk. So I have a comment and a question. The comment is just to say that actually the notion of setoid is mostly used because it gives quotients available, which otherwise you need to add to the theory somehow. And the question is instead about the definition of univalent displayed category. So I guess that's saying that the base is univalent and that each fiber is not enough.
No, it's we don't ask for the base to be univalent. Instead, we say that when the base is univalent, the displayed category is univalent, the total category is univalent. So there is a notion of displayed univalent by category or category, which does not involve the univalency in the base. And
okay.
it is
is it just saying that each fiber is univalent, or you need something like
No, is that you have an ID to ISO, a displayed version of the ID to ISO map, and you ask that this is invertible.
Okay, so for you consider each displayed arrow also?
Yes.
Okay, thank you.
So there is a kind of systematic way of displaying constructions. Every construction and theorem can have a displayed version in some way.
Other questions? If not, I have one. So at the beginning of the talk, you mentioned that one of the motivation behind all of that was the formalization of initial semantics, and you also mentioned the example of the lambda calculus. And then at the end of the talk, you said something about univalent bicategories of algebras for Can you tell me a bit more of how it works for the lambda calculus, for instance?
So the difference is that here is the difference is that here we are speaking of a language which is not a high order like a lambda calculus. It can do things like groups or
okay.
So
can't you choose a suitable pre-sheaves like nominal set
yes,
for doing high order things?
So the idea is that you can do that, but this is something that you can already do in one categories. And the interesting thing is that for untyped languages, the interesting thing that you can be very a very principled approach to use the same technique, but with bicategories if you have if you want to study typed languages.
Okay, but even for the untyped case, you can use a bicategory of relations, for instance, and
yes, of course. There are many things.
You use initiality for syntax, and then you have relations for equivalencies, and then you can also use initiality for modeling initial equivalencies and this kind of
yes,
things.
This is something that we didn't do, but yes, in principle.
Okay, thank you. Other questions? Okay, if not, let us thank again Marco.
Thank you.
Okay, and our next speaker is Sophie, right? Is it you? I think so. All right, so our next speaker is Sophie Despalong from the University of Lille, and she will talk about internal monadal structures in a day convolutional product. Okay, Sophie, please go.
Okay. So I was saying that I'd first like to thank the organizer because it's a real pleasure for me to be here in Pisa talking about categories. So we'll talk about internal monoidal structures and the convolution product in a monoidal 2 category. So the purpose of this talk is to define the convolution product in a 2 categories that is not the category of categories and understand what it means. So we'll talk about formal category theory internal structures in a monoidal 2 category, and we'll finally see how to extend deconvolution and what it means. If we have time for it, I'll finish by an example, but I'm not sure about it. So how does deconvolution product works? Basically, it just says that you can endow the category of presheaves over a monoidal category with the structure of a monoidal category too. You can just also notice that this construction also works when in the context of V-enriched categories. So how does it work? Take two functors or two V-enriched functors from C to a category V, and you just can form their tensor product and obtain another functor. And more generally, you obtain a monoidal structure on the category of presheaves. So is it possible to generalize this construction? And more precisely, which properties does the two categories and V-enriched categories share so that this construction is possible? Okay, so what do we need for this? So the construction on the left-hand side is made, as you can see, in the context of a 2 category, because you have just a 2 arrow, etc. So we need the 2 category. Also, we need to form some products in this 2 category. So we need this 2 category to be monoidal. We also need internal monoids in this 2 category. We need the notion of Ken extensions, and we need this thing. So what I call external product. I think it's often called like this, but what is the external product precisely? On the right-hand side, the notion of this external product becomes more clear. So we will see that, in fact, the external product of 2 functors just relies on the fact that the closed structure of the category of category is compatible with the monoidal one. So all of this lies in the context of formal category theory. So the principle of this is just to extend categorical constructions in a category that looks like the category of categories. So for instance, it has been made by Gray in Formal Category Theory, a book. So the notions we can extend are, for instance, adjoint morphisms and Ken extensions. So let omega be a 2 category. Ken extensions have been defined by Gray in 2 different ways. So you can define them locally, so just as an arrow together with a 2 arrows that is universal amongst some couples verifying some stuff. You can also define them globally. So when there exist, of course, you can define them as a left adjoint functor of another functor which is induced by a morphism in omega. So actually, you do not need the notion of adjointness inside a 2 category to define Ken extensions at this point. But yeah, and also notice that the global and local notions of left Ken extensions coincide in the sense that you just, the global one exists if and only if the local one exists for every morphism. And you even get a functor when they exist from the category of morphisms in omega to the category here. So the brackets just means the closed structure of the category of category. But let's get back at Ken extensions and deconvolution. Here you can see that the Ken extension we need is actually not a functor, but a V-enriched functor. So if you want to generalize the construction, you actually need the can extension to be defined as a morphism in U2 category and not as a functor. So I suggest to define internal left can extensions as a left adjoint of the equivalent of precomposition biomorphism, but in the closed setting. So these adjunctions, this time lies internally in the 2 category omega. I did not define adjunctions in the 2 category, but it is like you can imagine, just 2 morphisms with 2 arrows satisfying the commutativity of some triangles. Okay, and now if they exist along any morphism, it just extends again to a functor. Can we just have a link between the internal left can extension and the external one? So yes, in fact, since omega is a 2 category, we have a 2 functor that gives the category of morphisms between 2 objects. And this is the closed 2 categories in sense that, we have a closed structure on the product 2 category of the opposite category of omega by omega. We have a closed structure in the category of category, and they exchange via this morphism so that we just have a natural functor here, a functor which is natural in the variables. So thanks to this, we can make a link between the internal left can extension and the external one, and we obtain a commutative triangle, so that if you have a point, like an element that is a morphism from the terminal object to the object morphism here in omega, the internal left can extensions just coincide with the external one. Here, in fact, in the category of categories, those 2 objects are the same. And in the category of V-enriched category, you have an equivalence of categories because you can improve any natural transformations into V-enriched one, etc. So now we just have to talk about internal structures in a monoidal 2 category. So let omega be equipped with a 2 functor, which is associative up to an associator. Omega also has a unit here, and it is unital up to a unitor. So this is what I will call monoidal 2 category. For instance, you can consider the category of categories with the Cartesian structure, the category of V-enriched categories with the Cartesian structure too. In fact, if you take the category of monoidal categories, it is also monoidal because the Cartesian product is commutative. So you have a monoidal structure on the Cartesian product of 2 monoidal categories. We will see that, in fact, this isomorphism, which uses the commutativity of the Cartesian product, can just be replaced by a compatibility between 2 monoidal structures. Another example I'd like to talk about is the 2 category of sequences of categories with the composition product, operiodic composition product, in fact. So defined as follow. This is a 2 category that looks a lot like the category of categories, but that is not the category of categories. So now in a monoidal 2 category, you can define a pseudomonoid internal to it as just an object together with a composition internal to omega, a unit, unitors. I didn't write them, but they are just triangles and associators, 2 morphisms in omega that verify some coherence. You also can define pseudomonoidal morphisms between them. So as morphisms in omega, together with 2 morphisms, they are often called lax because this is not an isomorphism. and they verify unit and associativity conditions. So together with the two morphisms of omega that preserve strictly the structure morphisms, we obtain a two category of pseudomonoids in a monoidal two category. So let's give some examples. Take the category of categories together with the Cartesian monoidal structure, and its category of pseudomonoids gives rise to the notion of monoidal categories with Lex monoidal morphism. You can do the same in the V-enriched context, and I talked earlier about the monoidal structure in the monoidal two category of categories. Take the two category of pseudomonoids into it, and you will get the notion of twofold iterated monoidal categories. Those objects are actually really interesting, and you can iterate the process and to get the notion of n-fold iterated monoidal categories, which are just a categorical analog of n-fold spaces. So think of EN algebras, etc. If you take pseudomonoids in the two category of sequences of categories, you will get the notion of pseudo-operad. So pseudo-operad are two operads, what monoidal categories are strict monoidal categories. Okay, and the last example is a bit weird because if you take the two category of monoidal two categories and pseudomonoidal two functors, you in fact can obtain this two category as the two category of pseudomonoids in the two category of two categories with the Cartesian product. Okay, so we will need this example earlier to describe what is the external product I talked about earlier. So, and it is monoidal, these two category of monoidal two categories. So now, suppose our two category has a terminal object. Then you can define a pseudomonoidal structure in this terminal object thanks to the unique morphisms into it. And thanks to this, we will define the category of monoids internal to a pseudomonoid as the category of morphisms in the two category of pseudomonoids in omega from the terminal object to a pseudomonoid. So explicitly, a monoid internal to a pseudomonoid is just the data of a morphism in omega from the terminal object to our pseudomonoid. A two morphism that will play the role of the composition that verifies associativity and unit conditions. Some examples. When omega is a two category of categories, the category of monoids internal to a pseudomonoid, so in a monoidal category, is just the usual category of monoids in a monoidal category. If you take a monoidal category, which is symmetric and whose tensor product distributes over colimit, you can form the monoidal category of sequences of objects and take monoids internal to it, you will get the category of operas. Finally, this is, so if you take the two category of sequences of categories with the operatic composition product and the monoid into it, a pseudomonoid, you'll get a pseudo-operad, and then its category of internal monoids will just gives rise to Batanian's notion of operad internal to a category called operad. So an operad internal to a category called operad is just almost like an operad, but the airy operations just are defined in a category that varies depending on the arity. And then to make those operations together, you need to make them make it internally in your category of operations. So now we have almost all the elements to extend the convolution product. So we can we formulate the convolution for V-enriched categories for the moment as follow. You have a functor that, okay, the V-enriched category of functors to V, okay, the internal home gives rise to a functor that goes from the pseudomonoids in V-enriched categories with respect to Cartesian product to the category of pseudomonoids. Okay, it takes pseudomonoids to pseudomonoids. So we needed a two category with a closed structure, Ken extensions, a monoidal structure, and pseudomonoids with respect to it. The last thing we have to define now is the external product. So let omega be a monoidal category, which is Cartesian closed. You can write this for the internal home 2 functor. And as I said earlier, the two category of monoidal two categories is itself monoidal, so that you can ask this functor to be a pseudomonoidal functor. This gives rise to a morphism here, which I call the external product. And in fact, it just, yeah, so it's an exchange morphisms between two compatible structure. And okay, so thanks to it, we can just define the convolution. So the conditions we asked on the two categories that had to look like that now is to be monoidal, Cartesian closed, and the internal home 2 functor has to be a pseudomonoidal functor. So now take two pseudomonoids in omega with respect to the tensor omega, not the Cartesian structure. We can generalize the day convolution as the composites of the external product, then compose with the pseudomonoidal structure of V and the internal home structure. Take internal left-hand extension along the composition of the pseudomonoidal structure C, and you just get a pseudomonoidal structure on the object in omega of morphisms from C to V. Okay. This just defines an associative structure, which is kind of tricky to demonstrate because of the big diagrams, but it gives the object of morphisms in omega from C to V the structure of a pseudomonoid. So we obtain the same two functor we had. And we can go a little bit further and observe the following. The Cartesian product also defines the pseudomonoidal morphisms. So, because the universal properties of the Cartesian product just implies that we have some morphism here, which exactly says that the Cartesian product is monoidal, pseudomonoidal, so that it takes pseudomonoids to pseudomonoids. And since this commutes to the product also, in fact, the two category of pseudomonoids in omega is Cartesian. So, yeah, it is monoidal, in fact, and we can just observe that this monoidal structure is a Cartesian one. So, okay, as a conclusion, we can reformulate all of this and just say that deconvolution actually just says that the two category of pseudomonoids in a two category is Cartesian closed. So thank you for your attention, and
Okay, thank you very much. So questions?
Hi, thank you for the talk. Do you think it's possible to recover in this formal way also the universal property of the deconvolution structure? Maybe adding, of course,
which
assumptions on the
universal property of
Well, the deconvolution is not just any monoidal structure on a Presheaf category. It's the universal, it's the initial monoidal structure that renders a unit embedding strong monoidal. If you have a map,
yeah, if you have a notion of a unit in your two category.
Well, probably a little bit less. But do you think this is the?
Yeah, yes, because actually it's just defined as only universal steps because it's just an extension. So
Okay. Yes, I think this should be pointed out.
I'm
clearly
sure it
because
is.
it's a useful observation. Okay.
Yeah. Thank you.
Can I also ask another question? Do you think this can be extended to find also a formal presentation and maybe generalization for the substitution product? I think you call it operatic composition or something like that. Because this is something I believe is.
What do you want to?
You can define on the category of
if you want to define the composition product as a
I call it substitution. I don't know. Maybe you use operatic as a term, but you can define that in terms of deconvolution, as you.
Yes, you can.
Know. Can you do also substitution structures in a formal categorical way?
Yeah, I think so. I think you just need to. But I'm not even sure you need to the formalism here because you just have a category of Presheaves, right?
Well, but like, formalizing, this is a problem. This specific question I'm interested in because I thought about it for a long time and I believe it's a difficult problem to address. So if you have a solution for that, kudos.
I'm not sure I have the question. Just where did I? Okay, this one?
Yes, for example.
Yes.
Yes. In a sense, you would like to, as far as I understand, you would like to generalize that definition that is expressible in terms of deconvolution. So if you have a formal categorical way to write deconvolution, you can also quite likely write the substitution product. So it's good because I have reasons for using this in a formal categorical setting. So if you have a solution for this, I'm interested.
Okay, maybe
we can
we'll talk about it.
Yes. Just it's a bit technical, so yeah.
Yeah. Because I actually have an example with this at the end, but I'm not sure this is what you mean. But you can just consider just the operad of Presheaves over a categorical operad, and in this way, this just extends the composition product to another thing. But I'm not sure this.
Yeah, maybe it's not exactly. Maybe I see it's not exactly what I want, but we can discuss this later. Thanks again.
I just have a, perhaps you already mentioned this and I missed it, but is there some sort of guiding example that you had in mind that somewhat inspired this generalization that wasn't properly captured by the already available ordinary deconvolution?
Yeah, I had one. It's just, actually it is this one, just I wanted to define the operad of Presheaves over a categorical operad. And this case is just kind of particular because it's not like a V in which category you cannot, you do not have actually an object in the these two categories does not, the object of the two categories are not categories in the sense that you do not have objects, you have a sequences of objects. So the monoidal structure becomes really tricky to write. And actually, the composition just, I didn't really finish this slide, but this was my example at the beginning. And what we obtain is that we have the monoidal structure induced by deconvolution is this one. This means those things are sequences of categories, and they are endowed with the structure of a monoidal object, so an operad in cat, and the composition is just, yeah, it's given, it's kind of, this was my example, but
Thanks.
All right, so we are in perfect timing with the coffee break, so we can stop here for now, and we will back again here in 30 minutes. So let us thank again Sophie.
think so.
I can. I just turned it off again.
Now it works. Sì, sì. Ah, il nome lo sa ormai. Microphone is okay.
I microfoni
Is this
sembrano
okay?
So, our last speaker is Ruben van Bell, and he will speak about radon nicodym derivatives and martingales. So, please go.
Yes, thank you, and thank you to the organizers for organizing this event. So yeah, I'm going to talk about two things: radon nicodym derivatives and martingales. So those are things in measure theory and probability theory, and I'm going to try to say something about what's happening categorically with these two things. Okay, so the first part is going to be radon nicodym derivatives, and then the second part, martingales. So I'll maybe start with reminding you what radon nicodym derivatives are. So it's a thing in measure theory. So yeah, let's start with a measurable space. And let's look at two measures on this space. So a sigma finite one and a finite signed measure. And in such a way that this one is absolutely continuous with respect to this other measure. So what that means is the following thing. If mu of A is 0, then nu of A is 0 for every measurable A. Okay, so if that is the case, then we can represent nu in the following way. So we can, there exists a mu almost surely unique integral map such that we can write nu as integrating f over A with respect to mu. Okay, and this is the radon-Nikodym theorem. So then what are radon-Nikodym derivatives? So those are exactly those kind of f's. So that's the radon-Nikodym derivative of nu with respect to mu. And the notation for that is like this. So you can see the d mu's sort of cancel out. Okay, another way of looking at this is we can look at the following map. So if we look at mu almost surely, or equivalent classes of mu almost surely equal random variables that are integrable, we can send such a random variable to a measure in the following way. So again, by integrating over subsets, and that is going to be clearly absolutely continuous with respect to mu, then the radon-Nikodym term is saying that this is a bijection. Okay, so some examples. Why do people care about these things? So you can look at the standard normal distribution on the real line and the Lebesgue measure. The Lebesgue measure is sigma finite. Standard normal distribution is it's a probability distribution, so it's definitely finite. And is absolutely continuous with respect to lambda. So there is a density function. Of course, I guess in reality, you define the normal distribution using this density function. So you don't really need the radon-Nikodym theorem, but this is still a radon-Nikodym derivative. So yeah, it definitely is something relevant, these radon-Nikodym derivatives. Another example has to do with conditional expectation. So if we fix a probability space, so a set, sigma algebra of subsets and a probability measure on that measurable space, and if we look at a sigma subalgebra, G, so if we have those things and we look at a random variable that is measurable with respect to the bigger sigma algebra, then again we can define a measure by integrating over A's, and we interpret this as a measure on G, on the smaller sigma algebra. So okay, this defines a measure, and this is just other notation. So okay, so then we can verify our conditions from the radon-Nikodym theorem. So if your P of A is 0, then if you integrate over a 0 set, that's going to be 0. So okay, nu is absolutely continuous with respect to P. So that means there exists a P almost surely unique and now G measurable integral map F such that integrating over G measurable subsets is the same. And again, yeah, different notation, you can write it as this. And yeah, this F is called the conditional expectation of X with respect to the sigma subalgebra. And the notation for that is this. So that's also something that's used quite often in probability theory, especially martingale. So in the second part, we're going to come back to this. But okay, those are two examples of Rauter-Nikodym derivatives and why we care about them. So now I'm going to give a very short proof of a very special case of this result. So namely for finite probability spaces. So let's look at a finite set with a probability measure on that set. And let's look at a measure that's absolutely continuous with respect to P. Then I'm going to define a map F from A to R as follows. So okay, when this is not 0, we can divide by it, and otherwise, if P of A is 0, then Q of A has to be 0. So then we'll just take this to be 0. And then, well, you can just easily check or verify that this is the Rauter-Nikodym derivative. This gives you the map that you want. And yeah, because this is almost surely the inverse of multiplying by P, right? That's the reason behind it. Okay, so now I'm going to start talking about category theory. So the IDs, we're going to take the finite version and we're going to extend that to the general version. So the category I'm going to look at is prop as probability spaces as objects and measure preserving maps between them. Yeah, I'm going to define some things now. So fix a probability space. I'm going to call this space of all measures. And with measure, I always mean now finite positive measures that are bounded by n times p, and n is just a natural number here. And I can give a metric, so the total variation metric, so that becomes a metric space. And I'm going to call that mn of omega, where m stands for measure. And I'm going to define random variables on omega as well. So these are just measurable maps from omega to 0, 1, 0, n, and we identify them when they're p almost surely equal. That's a probability measure. Yeah, well, now I'm using probability measures. Yeah, so and this mu is a measure. So does that clarify it? Sorry, this one or?
Yes, the P.
This P is a probability measure.
And the other is another measure.
And this is a measure. Yeah, so the probability measure is fixed. So yeah, these random variables, we can also give that a metric, the L1 metric, and for some reasons we multiply that with a factor of half. And these are complete metric spaces. So yeah, you can use the Ries-Fisher theorem for that. Well, I guess that's sort of literally saying that these are complete. If we're looking at finite probability spaces, which is what we're going to do, then you don't need a big theorem, so then you can just prove that as a sort of an exercise. So I'm also going to define something on maps. So if I have a measure map between finite probability spaces, then I can define a map like this by pushing forwards every measure on A along my map. That gives you a measure on B. And I'm going to also define a map here by sending a random variable on A to this random variable that's defined in this way. And you can check that this is well defined. So if something is almost surely equal to G, then this is going to be almost surely equal to this one. And these are Lipschitz maps. Okay, so those were all definitions, but what did we actually define? we define two functors like this on finite probability spaces, two complete metric spaces. So then what did our finite version of this Radon-Nikodym theorem say? We can really interpret that as that these are isomorphic. That follows almost immediately from that. Okay, so now we have this, and now I want to Kahn extend these to all probability spaces. So that's what we're going to do, and well, because these are isomorphic, well, the Kahn extensions are also going to be isomorphic. So now we need to figure out what these Kahn extensions are. So yeah, if we fix a probability space, omega, then we have that, well, the measures on omega, like I defined before, are indeed, well, correspond as to the right Kahn extension of this functor evaluated in omega. Okay, so why is this true? So I'm first going to give like sort of an intuitive ID, maybe, sketch of the proof, and then a more detailed. So, well, for right Kahn extensions, we have this end formula, right? So if we ignore this integral sign for a second, then we have maps from this to this. And these are, well, since A is just finite, these are really A-indexed measurable partitions. And these are measures on A, but A is finite, so these are A-indexed real numbers. So we're sending, well, measurable partitions to real numbers, so that's already close to a measure, right? So if we then put the integral sign back, that's saying that, well, these maps are behave in a coherent way, and that will then imply sigma additivity. A more detailed version of the proof is, well, you'd first define maps from this to all these maps by pushing forwards along these maps from omega to A. Well, that gives you this map, or maybe better, this space together with these maps form a wedge over the functor we're taking the end of. So it's a wedge. Now we want to show that it's a universal wedge. So to that, take another one. And so yeah, that means we have map from Y to this for every finite probability space A, right? So it's for every finite probability space, so we're going to fix some special finite probability spaces, namely the following ones. If you have a measurable subset E, then we're going to look at this probability space where the underlying set is just these 2 points. And in that case, the indicator functions become measure preserving. Well, and then using all this stuff, we can define, we can assign to every measurable subset a real number. And then because this is a wedge, this is going to be, well, firstly, finitely additive, and then because everything is bounded by a measure, it's also going to be sigma additive, which is then going to give you the universal property. So that's very short, the proof, but I want to give you the proof to show that I'm not really using anything like special measure theory results or anything, just like sort of a straightforward categorical proof. Then for the second part, it does require some measure theories. So the second part is, or the second proposition is saying that we have the state for the random variables. So the right Kahn extension of this finite version of the random variables is indeed giving you the random variables that we want. And that does require some measure theory, which I'm not going to say more about, but yeah, the measure theory didn't just magically disappear. So that's sort of, yeah, going on here. Okay, so now we can combine all the things we have so far. So we have this space of measures. Well, that's by definition equal to this. Then we just showed that that's equal to this right Kahn extension. Then because on the finite level, they are isomorphic. Well, the right-count extensions are going to be isomorphic as well. And then with this last proposition, we have the last line as well. So that gives us the results, at least for when things are bounded by NP. So that's stricter than absolute continuity. But to fix that, we can take the co-limit over all n of both things. Well, the co-limits are going to be isomorphic as well. And that's then exactly going to be this. So then we have the Radon-Nikodym theorem. Yeah, so maybe to finish this last part, to finish this first part, a last remark. So, well, we described what these right-count extensions are doing on objects, right? But I didn't really say anything about what it's doing on morphisms. So, well, because they're right-count extensions, these morphisms are defined by a universal property. So it's these maps. Yeah, I use this notation to avoid writing right-count extensions the whole time. But these maps are the unique maps such that they commute for all, for a bunch of triangles. So because it's for all finite probability spaces, again, we can look at these sort of special kind of finite probability spaces, which we used before. Well, then these commutative triangles give us this. And if you then stare at these for a few minutes, then, well, you can figure out that that exactly means this. So we have pushing forward along G, and then these conditional expectations, which I talked about before. So that's, I thought was, well, cool that these appeared, because these conditional expectations are sometimes a bit difficult to work with, like the existence is not trivial. Usually you cannot really construct them. So I thought it was nice that they appeared from these universal properties. Of course, it's also not a complete surprise, because I showed you earlier that they do follow from the Radon-Nikodym theorem. But yeah, that's how conditional expectation also appears here. Okay, so to summarize this first part, we had a finite version of the result. We extended it to the general result. And on the way, we also found these, or recovered these conditional expectations. Okay, so that's the first part. Then the second part about martingales. So I'll start by telling what a martingale is. So again, fix a probability space and fix a lot of, or like a collection of sigma subalgebras that are directed, and in such a way that their union as sigma algebras, or their co-limit, I guess, is the whole sigma algebra. Then a martingale is a stochastic process. It's a collection of integrable random variables such that xi is only measurable with respect to this smaller fi. And such that we have this martingale condition. So taking the conditional expectation of xj with respect to an earlier sigma algebra gives you the earlier random variable. Okay, so these are martingales. Maybe to very quickly motivate martingales, why are martingales important? Well, the sort of the most important stochastic process, Brownian motion, is a martingale. So that's maybe a reason to motivate martingales as well. So what do I want to talk about for the last part now is this martingale convergence theorem. So I'll say what the martingale convergence theorem is, but I'll first remind you of this easier result that, well, every bounded monotone sequence in the real line converges. Then the stochastic analog of that is the martingale convergence theorem. So it says that if you have a martingale that's bounded in some way, it converges to something. There's a different version of that as well. If it's even more bounded, then it converges even stronger, and we can even represent xn as conditional expectations. So what does this mean in?
So can you go back one slide? Your martingales are indexed over n.
Yes, now
So
they
it's
are.
not like a continuous process, right? It's,
No, yeah, now I'm focusing on discrete processes.
and should I interpret convergence as some sort of a stationary condition after a while or something?
Sorry.
Like the fact that it converges to a random variable is telling me that the process is stationary after a while, like it becomes stationary?
Well, it's yeah, sort of convergence of functions, right? So it's almost surely pointwise convergence. Here it's convergence in a certain norm. So yeah, well, if this is constant, maybe then I guess you can interpret that in that way. But that limiting random variable doesn't have to be constant or anything.
Okay, thanks.
Okay, so in terms of category theory, how would we describe this? So all these sort of restricted probability spaces form this diagram. And then the space where we started with is the limit of this diagram. I think that's not too difficult to see. So now suppose for a second that that is Mn, just this functor of, sorry, this should have been an RV. Okay, so this M is an RV. Suppose that this RVn preserves this limit. Then what would that mean? Okay, first of all, it means this. And then this is a limit of complete metric spaces. So the way we can calculate that limit is, well, the underlying set is the same as calculating limits in sets. So then for any co-filtered limit of sets, you get something like this. But then a few slides ago, I told you that this RVn acts as taking conditional expectation, right? So that means this condition translates to this condition. But this is just exactly saying that our stochastic process has to be a martingale. So, well, we can interpret this isomorphism then as saying that for every martingale, such that they're all bounded by n, so we're still working with these bounded by n conditions, there exists something in here, a random variable, such that this condition holds. In the case where we're using this very strict boundedness, this condition will immediately, well, not immediately, but in a few lines of proof, imply the convergence as well. Okay, so what we want to show is that this RVn preserves certain limits. So the setting we have so far is not completely going to work. Well, it is definitely going to preserve these limits because, well, the martingale convergence theorem is true. So it should preserve limits, but I want to prove it in a more categorical way, right? So this setting is not exactly going to be the right thing. So I'm going to change things a little bit, but I'm not going to say much about it. I'm going to enrich everything over complete metric spaces. And then I claim that everything we said in the first part still works where everything is enriched over complete metric spaces. I'm not going to say a lot more about this except for something you might be wondering right now, how do I enrich prop over complete metric spaces? So I'm going to look at sets of measure preserving maps, and I'm going to define this pseudo-metric, so it's really a pseudo-metric. So I actually need to change this maybe to pseudo-metrizable spaces. And I'm going to take the completion if this is not complete. If our codomain is a finite probability space, and we have completeness, otherwise I take the completion. So okay. There's some details I'm not telling you, but modulo some details, this is still working in the enriched context. Okay, then the sort of categorical proof of this martingale convergence theorem. We always have, for categorical reasons, a map like this. Because remember, this omega was the limit of these omega i's. But in general, this is not an isomorphism. But in this case, because we're working in complete metric spaces, it is. So this is a co-limit of complete metric space. So that means we need to take a completion as well. So it's bigger than the co-limit of just metric spaces. And well, because this set is dense in this set, so that is by a lambda argument, you can prove that. It follows that in this case, in the enriched version of things, this is going to be an isomorphism. Okay, so what do we then have? RVN was this equal to this right Cannon extension, so this N formula by, well, what I said just now is we can take out the limit and that becomes a co-limit. Then for categorical reasons, this co-limit becomes a limit. And we can also take that out of the ends. And then we have, that this RVN preserves the co-filtered limits, which is what we wanted because that translated to the martingale convergence theorem. And then an interesting remark maybe here. I never really used anything special about this functor RVN, right? So I could also do everything for the other functor MN. That would also have given something, or well, other functors. So I guess, I found an interesting observation. And then this is sort of the final summary. So I'm going to stop here. Thank you.
Questions or comments?
Hi, thanks for your talk. I have two quick questions. The first one is on the first half of your presentation. It's a little technical thing, but I was a little bit puzzled. At some point, you have a colimit. Sort of, you pass something to a colimit to prove a statement. I think you have this subset of the measures that are bounded by NP, and then you take the colimit over N, and you stated that that's the same thing as being absolutely continuous. If I remember correctly.
That is what I said.
This one here. Is it obvious that if something is absolutely continuous with respect to P, it must be bounded by NP? Are these finite measure spaces or not?
So I guess I should have said I'm taking colimits in complete metric spaces again. So there's a completion going on. So I guess that's why we can push.
No, but even just in terms of measures, like if I know that mu of A is 0 whenever P is 0, like does it have to be bounded by NP necessarily?
No.
And so why is the colimit? Why do you get absolutely continuous measures if you take the colimit of those?
Because
things?
that's because we're taking colimits in complete metric spaces. So there's a completion. So it's not just a union, but it's like the union and then completed. So that's why
that's the thing.
More
okay,
than
okay. Because I thought it was just the union and it wasn't.
So there's this completion. Thank you. I didn't really say that, but that completion is giving us.
Okay, thanks.
This.
And the second one is you have this formal way of dealing with processes that are martingales. Can you also incorporate some drift in your processes with using this machinery, or is there something interesting to be done in that case?
I haven't really thought about that. I also don't really know that much about drift in stochastic processes. I don't really know the details about that, so I cannot really say anything useful about that. Sorry.
Okay, thanks.
Thanks for the talk. And I have a kind of related question. Are your metric spaced generalized metric spaces? Because I see you compute colimits, I guess, with usual metric spaces. You don't have all of them.
So I think.
So do you allow the distance to be infinite? I guess that's what I mean.
Yes, I think we don't need to. Maybe I've missed the detail, and we actually do need it at some point. But in most of the things, because we have this boundedness condition,
So yeah, maybe the limits are good enough so that.
Yeah, so the metrics are also going to be bounded maybe by 2n or something like that, or some function of n, so that you have diagrams that are where all the metrics are bounded by the same number, and then of course you can take
Okay, makes sense.
the co-limits. But yeah, otherwise I guess I should have worked with generalized metric space, but I think it should be fine like it is right now.
Thanks.
Other questions? I have one. In recent years, there has been a lot of work about new categorical approach to probability, using the language of Markov categories and their graphical formalisms. Do you think that it could be possible to present your results and instruments in this setting and maybe providing graphical proofs of these theorems?
So yeah, I haven't really thought about that, but I guess these conditional expectations are very similar to like the Markov kernels and the maps. That well, you think, you look at the maps in the Markov categories like Markov kernels, right? So I guess in that sense, you can maybe say something about a Markov chains and things like that. Maybe prove some convergence results for those as well. I wouldn't know what that looked like using string diagrams or something, but yeah, there might be something similar going on.
Thank you.
Yeah, just to add to your question, even if you don't look at string diagrams, there is this whole way of thinking about categories probabilities in terms of channels, states, predicates, like the work of Bart Jacobs and other people. And his work also, he has papers on this Radon-Nikodym theorem seen in that fashion. So I don't know if you're aware of these things. Is that something you've looked into?
About the Radon-Nikodym theorem itself, I haven't really seen much.
Well, I suggest you look it up because there are papers in which he proved, other people, including also myself, proved some results in this vein. And it may be just useful to compare and see.
Yeah, no, thanks. So, and that's Bart Jacobs.
Bart Jacobs, yeah. If you look up his page, there is all kind of papers that, and many of them have a good intersection with what you're doing, I think.
Okay, great. I'll definitely look that up. Thanks.
So let's thank the speaker again. Unfortunately, the other speaker is sick, so this was the last talk of today. So I want to thank all of you for being here, and Buon Natale.